Hello, everybody. Welcome to our latest ExoLife Hangout. My name is Tony Darnell. I work at deepastronomy.space, and it's been a while. This is like the first Hangout I've done since before Hurricane Irma, and we had quite a bit of excitement here in Central Florida over the past couple of weeks, but that seems to be behind us now. I have power and internet, which is always a good thing, especially in my line of work. So we're back, and today we are going to be talking, as we always do with these ExoLife Hangouts, about the search for life in the universe and the efforts involved. And in particular, we're going to be talking with usually they're co-hosts, but now they're kind of co-hosts and guests and sort of a jack of all trades in this hangout because they've written a paper. Jeff Kuhn and Svetlana Berdugina have written a paper on how to detect alien civilizations using the heat signatures on these planets, and we are going to talk about that today. And I put a link to that paper in our description box if you want to follow along, and I also have it where I will share our screen. But we are live streaming on the usual platforms: YouTube, Twitch, Facebook, and Periscope. So I'm looking at many of them now. I've already got the live chat up on YouTube, and seeing a couple of you there already. Dark Avenger and Alexander Reinders and Susan Hunter and Scott Cameron and others are here. So please leave your comments and questions, and we will read them as I and Kevin capture them in our browsing throughout the Hangout. So let me go ahead and bring up the other shot here. Here are my guests. In the lower panel is Dr. Jeff Kuhn. He's a member of the Planets Foundation. Also in the upper right is Dr. Svetlana Berdugina, and in the upper left is Kevin Lewis, who also works at the Planets Foundation. And before we start our hangout, Kevin, I want to give you an opportunity to talk a little bit about the Kickstarter campaign that you have going on with the Planets Foundation.
Yes, so we launched a Kickstarter campaign on September 5th to do a couple of things.
First of all, start by telling how they can get to it.
Okay, so I will put a link in the chat box right now. So you can either follow the link that we're going to post obviously in the description, or that's in the chat box, or you can just go to Kickstarter.com and search ExoLife Finder, and it should pop right up. We don't have a super short link. It's rather long.
Okay.
So yeah, we launched it earlier this month, and it's going great. We're about 50% funded.
What are you trying to do?
And, yes, that's what I was going to get into.
Okay.
So we're the goal of the Kickstarter is to fund. Let me get down to a new type of mirror. Which Jeff and Svetlana, actually, you wanna get into the metamaterial?
Sure.
You want to explain it a little bit?
This is the secret sauce. So mirrors for billions of years have been made by grinding glass, basically fracturing the surface and then removing those fractures with successively smaller abrasive particles. And it's a tedious, and we say it's non-deterministic because it's an art form as more of it's a scientific process. What that means in terms of money and the cost of a telescope is that it takes a lot of cycles of rubbing on the glass and cracking it and removing grains of glass, and then measurements. And a typical mirror could take dozens of cycles of that grinding and metrology. In a world where there's always a bright star in your field of view, which is what exoplanet studies are about, we can use the star to help define the surface of the mirror. And in the world we live in, where computers are cheap and it's possible to 3D print structures into a sandwiched material of glass, we can make mirrors that weigh less, never get polished, never get abrasively polished. Basically, it's window glass, which is really smooth. Mirrors for a long time are going to be made from glass. Glass is just a wonderful material for lots of reasons, and it's cheap and it's abundant and it's easily manufactured. And for optics, it's very, very smooth on scales that are relatively short. On longer scales, glass is rough and doesn't do what a nice astronomical mirror does. But that's where this metamaterial idea comes in. We take big pieces of glass and we print on the back of it a structure that measures forces and creates forces, and it looks at a star and it makes the star a sharp image, and that's your mirror. And that's the secret of everything that we want to do with the planets and the ELF project, and eventually the Colossus project, is to make mirrors much more cheaply and very, very effectively for doing the exoplanet problem.
Okay,
yeah, so the Kickstarter is to fund a prototype of this.
Yeah, so we need some seed money. We have partners that work in the field of, we call it muscle material, electroactive polymers, terpolymer. There's a group in Lyon that are our partners in the development of a mirror using this printed structure. It looks just like saran wrap, basically. It's a cellophane-like material that we print into the glass interstitial region. We put electrodes on it, and then we drive the glass, and we do it with an algorithm that looks at a star, so we know how to shape the glass and make a sharp, crisp point source, and that's where we need some of the seed money that we've been trying to collect by other means, and that's what the Kickstarter is about.
Okay, and where are you guys now on the campaign, Kevin?
Right at 50%. We have 183 backers, and we're about 50% to our goal with 18 days to go.
Awesome. All right, so please check it out, guys. These guys, the Planets Foundation, we're trying to raise awareness in part through these hangouts, and also through these Kickstarter campaigns, because they really are trying to do some important work that is really no one else is even looking to do. And as Jeff pointed out, they need some brand new materials that don't involve grinding mirrors. And coming from someone who's actually done that, I can tell you that it is in fact an art. I have sat there in front of a mirror grinding and using different abrasives and trying to get a spherical curve, then turn that spherical curve into a parabolic curve. All of it was magic. It really was. And the fact that my mirror focused anything to a point at all was nothing short of
How big was your mirror?
8 inches. Yeah.
Wow.
Yeah,
you're good.
I did this back in like the early '80s, and yeah, it was a good learning experience. I still have the mirror blank, but I don't use it much anymore. But yeah, it was a good experience. And in fact, if any of you want to know what it's like to make a telescope mirror, it's a good exercise to go through. I'm sure somewhere you can get abrasives to do that. Okay, so let's get to today's hangout, and the topic, as I mentioned before, is detecting extraterrestrial civilizations using heat signatures. And in fact, David Chapman is asking, how does heat output tell you there's a civilization on the planet? Which basically cuts right to the chase. So let me show you this. This is the paper that they've written, and I'm going to have it up periodically to refer to global warming as a detectable thermodynamic marker of Earth-like extrasolar civilizations. The case for a telescope like Colossus. Okay, so who wants to give me a summary at first, and then we're going to dive into, just give us a big picture overview of what you're trying to do with this. I guess it's an algorithm. Is that right, Svetlana or Jeff?
Try that to summarize shortly.
Okay.
Yeah. So how do you look for civilizations? We discussed it, like how do we look for life if we don't know how life outside Earth looks like, whether it is the same as ours or not? Well, the same question here. How do you look for civilizations? If they want to communicate, they don't want to communicate, they have chemical life, or they don't, or they have just robots there on the planet. How do you actually search for them? So the basic idea that everything in the universe we know is driven by physical laws. And very important law is the second law of thermodynamics, which says that you cannot use energy without losing energy. So there is always non-efficient amount of energy unused, which is deposited into the environment, whatever you do. So that's the idea, that we search for some activities on exoplanets which are definitely not natural, and which cannot be produced by natural phenomena, but they are excess of heat. There is an unnatural excess of heat on the planet. And in what we compare again is our planet. So we have these unnatural sources of life, of signatures of our civilization. These are our cities. So the picture what we have in the paper, that is, I mean, like really summarizing the idea, I would say we can go into details, how we model this and so on. This is the picture number 3. Picture number 3. If you look at this, this is a temperature map of...
This one?
No, the green one down there.
Oh, further
More
down?
down. Yeah, further down. Yeah, this green one. Yeah, small one.
Okay.
So that is like, okay, what is that? The temperature map of urbanized area of Midwest, it's called, yeah. And those red spots, these are our cities, and they are differ to the surroundings, like 10 degrees Celsius. So the green surroundings is about 24 degrees, as you see, and the red city spots, 36. So 10 to 12 degrees, our city is hotter than the environment.
So the green, would the green then, Svetlana, be just sort of the planet, the ground heat, and then the cities themselves, the yellow areas are slightly warmer, and then the cities themselves being the hottest? Okay.
Yeah, look at this. Downtowns, Chicago, Detroit, and etc., they are extremely hot. The same Paris, Atlanta, there are this huge Tokyo, all these huge multi-million cities, they are enormously overheated compared to the environment. And that's the idea. We cannot avoid this heat. It's unavoidable. It's unavoidable heat, and it's unintentional civilization signature. So in summary, that...
Okay, so... Okay, well, hang on, because I just want to kind of drill down. I want to give make sure I'm getting the scale of this. So already you look at a star, it's very bright, but it's not good enough. We have to block out that star and see this planet that is billions of times fainter than that. So we want to see, and just seeing that is hard enough, but embedded in that signal of the reflected light is something else even more faint, but you want to pick out of this, which is what you said it was it was greater than the natural heat, elevated temperature of what would be there naturally. My gosh, I mean that sounds like a tiny effect to me.
It's detectable.
Let me jump into that,
okay, go
Tony,
ahead.
because you're right. It is small, but it's much. People talk about, for example, well, suppose you had a civilization and they had lights on at night. Let's look for their lights, because we've all seen pictures of the planet. And you see the light that shines out into space from our street lights and our car lights, and that's a signal which is hundreds, thousands of times less than the heat signal. So I think the main point here is that all life is about energy, right? Life requires energy to exist.
Okay, so here's what the Earth's doing.
Yes.
Right?
What people do, yes.
This is what we're doing. Invisible light, which isn't infrared, but it is visible light, and optical. It's quite a bit of an effect. Everywhere where there's land, with the exception of maybe the Amazon and some parts of Africa, are all pretty bright. Look at India. Wow. So I mean, this is the effect you're looking for.
Well, except that we can't see the light, and it's about energy, and the reason is that even just a little bit of reflected starlight off of the planet, just the reflected albedo of starlight, ends up completely swamping the signal from lights of an industrial civilization. There's a very general argument that says that any life creates heat. I mean, think about the movie Alien or the Schwarzenegger movie, and that the signal that pointed out alien existence is a thermal signal. The total, and so here's a way of looking at that the fractional change in the infrared brightness of the whole Earth due to our civilization, in other words, how much thermal energy does our civilization, humankind, produce compared to the total thermal energy of the Earth, that's the background, is at the level of a few hundredths of a percent. That's not a hard signal to measure. Astronomers go out and measure signals at the level of hundredths of a percent of a background signal. And that's the point, that if we separate the starlight, right, we have to see the planet outside of the glare of the star, and that's why it takes a big telescope like L for Colossus. That's why we're talking about telescopes. But then the signal for the existence of life it depends on the advancement of the civilization. So throughout human history, we have advanced in the amount of energy we produce compared to the background energy. So if you go back to Roman times, the number wasn't 10 to the minus 4 of the background energy, it was 10 to the minus 7 of the background energy.
Yes, and just I chip in, there's a question. If the other civilization stuck in Iron Age, how can we see it? And that's the answer. We won't probably see them because they're very low on energy.
That's right. Although, right.
Well, okay. So I would, before the go ahead, Jeff.
No, I'll wait for you.
I was just going to say, before the hangout, I looked up a few things, and according to your paper, you said you were, I think, starting with what you called what's known as a type 1 civilization. Is that right? You were thinking, because in terms of energy output, your algorithm could detect something along the lines of a type 1 civilization, which the definition of which is that it can harness all of the light energy that falls on the planet from its parent star.
So remember, there's this Russian guy, right, who said, okay,
Kardashev, yeah.
Kardashev said that, how did you pronounce
Kardashev.
it? Kardashev. Kardashev. Okay, I always say Kardashev.
I do it wrong too, Jeff.
And so what right, a civilization that uses all of the energy, which is the starlight that strikes the planet, is type 1, and sort of pre-type 1 is what we are. We're not using all of that energy. A civilization that uses all of the starlight produced by their star, not just the light that strikes the planet, but all of the starlight, is type 2. And that's this idea that maybe Dyson spheres could capture all of the energy of a star and use it for the purposes of a civilization. And so there are searches for the type 2 civilizations that we've talked about. And type 3 is a civilization that somehow uses the energy of a galaxy. And that's this godlike idea that is even beyond that. So we're pre-type 1 because we're not using all of the energy, but surprisingly, we're using 10 to the minus 4 of the sunlight that strikes the Earth for our purposes. And in other words, if you took all of the energy that we produce, and the point that Svetlana made was that if we do work, any amount of work that we do, running a car, listening to a cell phone, running our computers,
air conditioning, think about that.
Air conditioning does work, creates heat. It creates
computers.
Yeah. And so it's that thermodynamic principle that says, let's look for the heat as a universal signature. Yes, methane is a great source of it's a biomarker.
Biological, yeah.
They're biological markers that we could also look at for more primitive life. But ultimately, the signal, even the Amazon forest, is a thermal signature that we would look for. Now, you can say, well, how do you find a thermal signature when there are volcanoes on a planet, or the albedo variations in a planet? In the paper, we talk about that. Yeah. There are ways of life, if it's to be most efficient, is probably going to operate at a temperature just a little bit higher than the ambient background.
Okay, so were you, for the purposes of this paper and simulation, were you starting with the assumption that you were going to be looking at type 1 civilizations then for power output?
Yeah, we asked the question, as an astronomer, if you're looking for a heat signature, how low could we go? In terms of
what is detectable? Yeah.
Yeah, in terms of the total energy that a planet re-radiates. So the Earth collects energy from the sun and heats up and then radiates a lot of thermal energy. And on top of that thermal energy is a little bit of a perturbation that we could see as a time-dependent perturbation. So in the paper, we're using the rotation of the planet as civilization, and the inhomogeneity of the civilization rotates so that the side of the planet...
the assumption that civilization won't be homogeneously distributed over the planet. So let's say, it's not so overcrowded yet. And that's this kind of assumption, but it also means that it's not that super advanced civilization which uses all the energy which arrives to the planet. What we found out that actually we don't need such advanced. It's class 1, type 1 civilization, but it's not yet super advanced that they don't use that all energy. They use significant part of it. But
so it could
all.
be close then to that level, to type 1, but maybe not type 1.
It could be.
Too
So
Well,
here's the problem.
It's not. There's not like a sharp demarcation line that says we're now at type 1, and so here we go.
Exactly.
We can now be detected by Jeff and Svetlana. No, I realize that, but
the paper argues that at the level of 10 to the minus 2 of the total energy that a planet radiates, we can see that, we can find it at a fraction of a percent.
Yeah.
A fraction of a percent.
Half a percent, I think.
And with bigger telescopes, we could go further. This was to talk about things like Colossus.
Well, but before LIGO, I would have said you guys were crazy. But after seeing that signal, it's like, wow, this is you can do this. You're right. That's actually not.
What we're talking about is so much easier
science
than
fiction.
LIGO.
And that is
so much easier than LIGO. But so I wanted to respond to some of the questions that Kevin is putting up here. So Philip asked, how can we distinguish the heat of volcanoes, for example? And the point is that the geothermal things are very hot. And so when we measure this signal at a couple of different wavelengths, say 5 microns and 10 microns, we can actually measure the temperature as things rotate into the field of view of the telescope as the exoplanet spins. And so we look in the visible, we look at 5 microns, and we look close to 10 microns, and the ratio of those wavelengths tells us the temperature. Now we could always be confused, right? A planet like Venus, we can't see through the clouds. So there are false.
There are limitations, yeah.
Yeah, there are limitations, but in terms of the most general way of finding life, it's heat. Life is about heat, and it's about heat near a temperature of the ambient temperature of the planet, below the boiling point of water.
I want also to go to the next question. Ivan Mitriev asks that whether it's if civilization destroys itself, okay, fine. But if they switch to environmentally friendly energy, it doesn't matter. You still use energy. However environmentally friendly you are, you collect energy. Imagine you go all for photon energy, solar energy. You collect energy, you use it, and some of it you deposit into environment. The more you use energy, the more you deposit.
But
so
maybe,
it doesn't matter.
Maybe yes? Ivan's comment was that one solution to so we were talking about omega equals 1 civilizations. They have a real problem. If they're producing
global warming,
if they're producing energy from stored sources or from radioactive sources or fusion or something, then they're going to heat up their planet. It's inescapable. That's the inescapable global warming problem.
Unavoidable, yeah.
But if a environmentally friendly planet, and this is what we actually should be looking for and are looking for, actually captures the starlight before it heats the planet. It uses that energy to power their cell phones or do their computations, and then returns that work to heat in the environment. Then they can do work with all of that power at omega equals 1, and they can heat the planet as long as they're using the energy only that's coming to the planet due to the star. Now, the other question about, well, would a civilization snuff itself out if it somehow found some other means of existing? The change over time in our power usage is such that per individual, we continue to increase the amount of power that we use. And even if you go to the limit of, well, we're not actually transporting material and we're not actually we're not moving things a lot, so it becomes an information world. The act of moving information, think about your computers, is an enormous power source. And in fact, the fraction of power that humankind is using for information processing is a rapidly increasing curve.
Yes.
So information manipulation itself, for very general arguments, uses power in the same way that it takes power to propel a car from here to the other side of Maui, where I live. so again, I think that ultimately the biomarkers that will be most general for this detection problem are going to be related to heat, and in our case, thermal signals, because it's heat at temperatures near the liquid point of water.
All right.
Well, that's not all that's going to be used, though, right? I mean, you have your heat signatures, you make your heat maps, presumably, but then you're also going to be looking at, you want to be seeing some spectroscopic observations too, right? I mean, you want to see some of these other
Yes.
follow-up ground truth kind of observations. So okay, well, do you guys want to keep reading some questions, or do you want me to go where I was going to go next?
Yeah.
I can't remember. I don't know which ones you
There
read
is
already. So.
there is one question about energy resolution and angular resolution. So I understand that energy resolution is sensitivity, and our civilization produces this 10 degrees Celsius, let's say, difference between towns, and it's increasing actually, maybe 15 sometimes. So, but as Jeff said earlier, it should be temperature difference, which is which we can, how did you say that? We can tolerate, yeah. So we can tolerate that heat. So it's still comfortable for us. Or we run these machines like air conditioning, which help us to keep the tolerant temperature, which produce additional heat into the environment. So this sensitivity of a few tenths or 10 Kelvin or Celsius is the same in terms of delta. That sensitivity we can achieve by using different measurements at different wavelengths. And Jeff said 5 and 10 microns, that's what we propose. Seems like working pretty well on that. And angular resolution, we will not resolve directly the surface of a planet. The planet is still too small to resolve it as an extended object with our even big telescopes. So we will use the techniques to obtain this indirect imaging information. So as again, we explained that planet rotates and you see the modulation of the thermal energy from a planet, and we will use this to map the planet to convert that temporal variations into spatial variations. So that's the idea. And angular resolution of that is not like really small, let's say, but it's comparable to it's smaller than the size of continent. So that's why civilization has to be a little more advanced. So cities should be of several thousand kilometers urban area, kind of like that.
Okay, and so you keep going with the telescope requirements, like you outlined in your paper. What sort of telescope do you need to be able to do this?
Well, we want to measure thermal heat, and we want to measure some optical reflected light. So they have to be sensitive in the infrared, about 5 and 10 microns, and in the optical. And they have to be big. So
Right.
we propose Colossus as the main telescope for detecting civilizations.
And remind us again about the characteristics of Colossus, because not everybody may have seen those hangouts.
Right. Colossus telescope is 75 meters in diameter, consisting of 60 roughly mirrors of 8 meter in diameter. So it's scalable, can be bigger or smaller, but that's what we propose for this kind of project to measure the civilization signals.
Okay.
But the idea was that so here's the background idea that if you make a telescope big enough, you can bring these ideas that are sort of philosophy and sociology, and you can make them science. And the notion is that we could take a census of the nearest several hundred exoplanets if you could create an optical system that's about 75 meters across. And the justification is we now can take not just exoplanets, but exolife into the realm of statistical studies, where if with a telescope that big, we don't see any evidence of life and it'll be about 300 stars, then we should start to worry about whether or not life really is robust.
Yeah,
you can make. Yeah, go ahead.
Well, I just wanted to compare that with what SETI's doing. I mean, SETI is they're doing a similar survey with statistics and stuff and looking at different wavelengths. And your method would be, it sounds like you're thinking would be more promising? I mean, how would you characterize it in comparison with what's being done by SETI now?
Well, SETI has the potential for looking far out into the universe with a civilization, for example, that beams laser signals, and they just happen to cross our path. But SETI has built into it some assumptions about the sociology of life.
Of communications, yeah.
And,
they look for communication
communication
signals, yes, also. So it's assumption that civilizations have to communicate in order to detect them. And in our method, the technique, what we propose, it doesn't have to be communicating. It's no need. It just has to exist and be active. That's all.
And not do any sort of broadcasting in any way whatsoever.
No TV, no radio. Be yourself and just do your exercises, and we see you.
But if civilizations are common in the galaxy, then the chances that no one is doing that, except us, is a little silly. I mean, we're, of course, some might not. You don't have to say none of them are. But, some, I would, who knows what the fraction is of those that do versus those that don't broadcast. But what you're saying is you can't hide these broadcasts, right? What this heat is something you simply cannot mask, or you cannot choose not to do.
Communicate.
Your assumption is that if you're a civilization of a type 1 level, you're putting out, let's see, let me pull up my Wikipedia page. You're pulling out something like 10 to the 16 watts of power. By comparison, we're only putting out 10 to the 12 watts. Let's see, what is that? A billion is 10 to the 9, trillion, 10 to the 12 is 4 trillion watts is what we're currently putting out. And a civilization like that would put out 10 to the 16. What is that? What comes after trillion? A quadrillion? So 16, so quadrillions versus of watts cannot be hidden. That they cannot just choose not to do that. So that is where your system might be a little bit more robust compared to SETI, among other ways. Right?
Well,
am I getting this right?
I'm not ever going to argue that we don't want to be doing radio searches for communication signals in the universe.
No, I'm not saying you are arguing that. I'm just trying to compare it.
I think, yeah, your comparison is a good comparison. That right, the total energy that our civilization puts out in radio broadcasts or in any kind of coherent signal is billions and billions of times less than the thermal signal that we radiate. So we depend on... And
there's also line of sight issues, isn't there, with SETI? So, I mean, we have to be...
Well, yeah, we have to depend on the fact that our radars are looking in the right direction at the right time, and that we're getting... I mean, the radio leakage signal that you're talking about, say, from television broadcasts, doesn't have an enormous reach, and that's a hard problem. The new area of SETI that is this realm where we're looking for optical communication or optical propulsion schemes, like what Breakthrough is doing, is perhaps has a chance of a greater probability of those detections. But it's different. And it could well be that is ultimately going to be our first detection of a civilization. But I think what we're trying to argue through the Planets Foundation is that there's this other problem, which is, let's look at the atmospheres carefully to do chemistry in the atmospheres, and let's look at the thermodynamics. Let's map the surfaces of these exoplanets to learn about things that you can't easily hide.
No, I like that. I like that a lot about your method here, is that it's something that if they're there, they're not going to be able to hide it. And I think if we're looking at the right spots, you can see that. Which brings me to my next topic that I want to ask you guys. Let me pull this up. This is in your paper. Where would you be? Let's say you had this thing up and running, the Colossus, and are these places you would like to look for these civilizations?
This is quite interesting you put it up, because this paper was written in 2015. I mean, we started to work earlier, published 2015. So Proxima B was not discovered yet, but we put the Alpha Centauri A, B, C habitable zone planets. So C means Proxima. So now we have this habitable planets over there, and we have it on the list. And, so we actually... we know that there must be planets, so there will be discoveries also around A and B planets. We count on them because these are the closest stars with closest exoplanets, and of course we look at them. But again, we can look, like Jeff said, and there's a question, with this size of telescope, we can look at planets within about 60 light years, several hundred stars with several hundred planets there. And first, we'll see what it all on those planets. Like, is there atmospheres? Is there liquid water? That's the first thing we will see. And then maybe we'll look some signatures of primitive life. And after, or simultaneously with that, we'll start to look for civilizations. You know, this is, and again, like, it's not just one technique which solves all the questions. You really, all techniques we discuss, they're all complementary, and you need them. Like we do in science, we find one thing with one technique, then we look at the same thing with the other technique, so that we say, yes, these two things are compatible, you know, and we reconfirm this continuously. So we'll do that with civilizations and life, same way.
Now, in your one of the first hangouts we did together, you guys had a technique for mapping the actual surfaces of exoplanets that just astonished me. And to do that, you ran some simulations to get the effect that how your algorithm would actually do in measuring with actual data. Were you able to do that with this method? Were you able to run any simulations or plot any?
Not yet.
Okay, all right. I wasn't
yet.
sure because those are.
This will be the next exercise. Yes.
Well, there's a difference also in that.
Yes.
So the mapping technique that uses reflected starlight, and then we watch the planet as it orbits and as it spins to get the surface map, depends on the fact that the starlight is coming at a different inclination and illuminating different parts of the planet as the planet goes through its orbital seasons. In the case of the light, which is the thermal emission of the planet, we don't have that changing orientation of the axis.
Okay.
So the axis with respect to the Earth and our telescopes is fixed. So that means that we can make maps, but the maps are going to be, we don't have any latitudinal information. It's basically just longitude information that will come out of those thermal maps. And in fact, so the measurement is to look at the time variation of the total integrated light. And that's where the signal is. We can make maps and they would be interesting, but more interesting in those cases where we see the thermal signal will be also to look at the reflected signal of the starlight, because one of the signatures of an advanced civilization will be their ability to shape the surface of their planet. And so by making a map, for example, of the surface, we'll be able to see where agricultural zones are laid out as a function.
Are you talking about a map like this, sort of the reflectivity? This is the albedo of the Earth.
Probably a much lower resolution, than this one.
That albedo map is instructive, and I would suggest that for an advanced civilization that's most efficiently using its land and water mass, there'll be structures, superstructures on the scale that we can see them from our mapping technique. So one of the interesting signatures of advanced civilization from the mapping point of view will be structures that extend over large scale. I mean, think of the Great Wall.
Like panels, photovoltaic panels, like fields or something like that, yes.
Right, and I think we didn't say finally what the ultimate answer is for a civilization that's very eco-friendly. It will be a civilization that has large regions where the albedo is very low. The albedo means that they're collecting the energy,
that's right,
and they're using it. And
okay,
so
let's talk. Yeah, let me just explain this a little bit. Albedo, folks, if you don't know what that is a measure of how reflective or how bright something is within reflected light. And this area around the equator, it's dark, not a lot of reflectivity going on. The poles are much brighter because of the snow. And what you're saying, Jeff, is that if a civilization is environmentally friendly, like we're hoping to become in the next decades coming, in this next century at least, then there'll be areas of more darker areas where you
Yeah,
live.
Yes.
look at, I mean, one example, look at Sahara. It's kind of brightish on this map,
Right
yeah?
here, yeah.
Imagine, there are plans to cover Sahara plain by all this photovoltaic system. It will be dark because they will absorb light. So this will reduce the albedo of Sahara
I
in
know, but
this
wouldn't
way.
you kind of need a before and after picture, because you wouldn't know what would ordinarily be bright without those reflective panels there or absorptive panels there. I mean,
No,
you
but
see,
imagine that if you looked at the low latitudes in a planet and you found these bands,
yeah,
well-defined bands of low albedo, that's a pretty big
Yeah,
hint. And
okay.
I think that it's that variation and the variation with respect to, for example, the continental areas.
And it might even have a much more defined structure, that actually a pattern that looks
yeah,
artificial and not so
yeah.
natural looking too. That's interesting.
And you
Huh.
can see it in the reflected light for sure. This is also what will be part of our paper.
Okay, wonderful. Do you guys want to get to Plastic Scally's comment? I can read it if you want. Can anyone tell me the biological and chemical signatures we would see in an advanced civilization? That's not what you're talking about. You're talking about heat and infrared. But what about biological and chemical signatures? What would you expect to see in an advanced civilization?
Yeah, we talked a little bit on that.
Right.
There are suggestions that freons are signatures of industrial activity and pollution of the atmosphere. Some gases, aerosols, some macromolecules which cannot be produced naturally. They can be detected in the atmosphere. This would be technological chemical signatures of civilizations.
But at a lower level, oxygen, except in some funny chemistries, is
This is
also
biological. Yeah,
a biological
yeah,
signature that we care about. Methane is a transient, and the
yeah.
existence
The
of methane at some
biological.
level.
Yeah.
So the idea is, once you have a telescope this big that it can see these thermal signatures, the spectrograph that goes on the telescope is going to tell us a lot about the
Mm.
chemistry of the atmosphere, and we can begin to cross-reference all of the signals that we have to get
Exactly.
a
And this
picture of
is
what life looks like.
once you have a machine like that, you really look at everything. You look at atmosphere, you look at surface, reflected light, thermal signature. You start to figure out what's going on the planet. It's like we're peeking into life there. Or, I mean, life in sense like what's going on, what's up there, you know?
Yeah. Oh, here's a good question. Primoz Verdnik. What about heavily clouded planets? That's a good question. What about if you're like
Yeah,
managed to somehow be a Type 1 civilization in Venus, let's say? I don't know how you do it, but let's say you
yeah.
could. Uh, would you miss those, do you think?
That would be hard. Yes, clouds are really. I mean, imagine if like planet like Venus covered by clouds. Sure, what do? You see nothing. You see clouds. Whatever happens on the clouds, you need a radar, like we do with Venus, radar or lander. Yeah. But one idea we have also in our other paper we finishing now, is that yes, you live on the clouds and you want to harvest the light. Yeah, you want to harvest the energy. What do? You put these panels above the cloud. So you have a system of
Oh.
absorbing light panels around the planet. It's like a kind of Dyson sphere, can be Dyson belt or whatever. And that structure we can really see very well, because in contrast to clouds, it will be much darker, and that's a very detectable signature.
And yeah, and presumably more regular shaped or in some kind
Yes,
of some,
absolutely.
yeah, yeah.
We made simulations of that, and it works very
So you're
nicely.
kind of
So
hoping
clouds,
some Type 1 civilization
yeah,
does that kind of thing
exactly.
on a
So you
clouded
live
planet.
on Venus, you want to harvest the sunlight, you put the things above the clouds, and that's what we detect. So
Okay.
not completely lost case.
Okay, I want to get to this question by Maxentius, which is asking you about the Colossus design. The planet's website states that Colossus design is scalable, meaning that it would be possible to construct an array of colossi.
Right.
How far would that
Next
expand the
stage.
search radius? Could you like build more than one of these and connect them up?
Yes, we fill Sahara with all colossi we want,
I think you'd be happy with one, I'm sure, but
That's our dream.
what
That's
did you
our
mean by
next project.
scalable? First of
Next
all,
Kickstarter.
well, what did you mean by
So,
scalable then? In
so
that,
the idea of in order, the astronomy community it's going to be a long time before we build a conventional telescope that is as big as Colossus. It's sort of tens of meters across, 70 meters. The largest telescope that astronomers are talking about building is the extremely large European telescope, which is 39 meters, which is multiple billions of dollars, and is not a very good telescope for doing exoplanet studies because of the way that it's constructed. It will do exoplanet things, but not like what we're describing. So the idea of these telescopes is that each telescope unit you make out of a piece of this active metamaterial glass as big as we can make it, and it has its own secondary. And the telescope is actually a cross between what astronomers call an interferometer and a telescope. So that as you add new units of telescope plus its secondary, you combine the light coherently to create what ultimately becomes the signal where we look for life. So the telescope itself can be grown. We can add extra units to it because each one of them doesn't change the way the telescope fundamentally works. And it's this cross between interferometry and a telescope. The answer to your question of how far out can we see is an interesting question, because the number of exoplanets a telescope can potentially see grows with the diameter of the telescope to the 4th power. That's an interesting thing. So that means that if we could double the size of the telescope effectively, go from, say, 50 meters to 100 meters, we could increase the potential number of exoplanets by a factor of 16, more than an order of magnitude. So this is a problem where size really, really matters. The size of the telescope is what essentially provides the reach into the universe, the distance from where we are, and it relies on this sort of idea that crosses elements of interferometry with elements of conventional telescopes, and it's the size that really matters. Now, I should say that that's also the reason why going to space is a really, really hard thing to do, because it's the size of the telescope more than anything else that matters for this.
And getting something that large in orbit is really hard.
Yeah.
And expensive, super expensive. Then it's not just billions, it's tens of billions.
Mm-hmm. Right. Well, we made the case early on, folks, and I'd encourage you to watch some of the earliest ExoLife Hangouts where Jeff and Svetlana talked a lot about these telescopes and what they're hoping to do with them. They're coming in various stages. The ExoLife Finder telescope, ELF, is being built first, and then they have these other stages along the way. So we've got a lot of good information on what these telescopes will hopefully do for us. And we've also had discussions on how hopeful we are that we're going to be able to actually detect any life with these planets, and that's important. They're not just trying to find exoplanets; they're trying to find life, and so this is an interesting problem, and to do it from the ground and the way they're doing it, I think, is absolutely fascinating. Can you give me some comments a little bit? How about what do you? I know we've talked about this before, and I don't want to go into it too much, but I love to get your opinions on how common you think life might be with this, and how hopeful you are that you're actually going to find anything. Because the more I do these hangouts, and the more I talk about life in the universe, the less hopeful I become. And you guys are always very optimistic. I hope.
I hope we disappoint you. Don't disappoint.
No, I hope you don't. I hope you win. I hope you win the universe, because I want this to happen. But I don't know. We live in a golden age of astronomy. We've talked about this dozens of times in these hangouts. We've got the detection capabilities unlike never before, and still nothing. And I don't know. I'm just.
Well, that's why. Yeah, we look for communication signals with SETI for decades. We find nothing, and then we start thinking, okay, what do we do? What is wrong with our strategy? How can we change it? What's wrong? Is there civilization not there, or maybe we just search it differently? That's why there is now this kind of plethora of ideas how we can search, and we also come up with our own idea on this thermal signature of unavoidable signal, and in the beginning also what we say is that it's really like the less assumption on intentions and social structure of those civilizations you make, the more probably
Okay, Svetlana, but
chance
you
to
were
find
guilty
it.
of it in this
So
hangout
can I?
yourself. You said yourself on a cloudy planet they would put these things above the clouds.
Oh well,
You don't know they would do that. They could choose not to do that. You know, so
So
they may not,
so
yes, they may not do it, but they want to
let's
have
work on
light.
let's work on Tony a little bit. So Tony, here's how we can balance your pessimism. So the first point I would make is that let's talk about ecologies rather than individual species. And ecologies are incredibly robust. You can't kill them. We've never succeeded in getting rid of ecologies. In fact, we find out that life exists in unimaginable circumstances.
well, what scale are you talking about?
So,
Planetary scale?
well, just life in general. All right, that's the
Okay,
first
sure,
point.
sure.
All right. Now, so the next point that took me through my thinking was that every time we've said we're somehow unique, center of the universe, center of the solar system, center of the galaxy, there are no exoplanets in the universe. The only place where we can make planets. When I learned astronomy as a graduate student in a physics program, but there were, God, I had courses from brilliant people, not Chandrasekhar, but Martin Schwarzschild, right, and Lyman Spitzer were teaching, and they said, we kind of think that planets are to get a planet to form around a star is pretty hard, and that it's not very likely. And within the last 25 years, our lifetime, our generation, there are more planets in the universe than there are stars. Now, okay, so that doesn't prove anything, but it does give an example of this problem that we have in human perception. Now, there's another problem in human perception, which is that we're taught from the moment we're born by our mothers that we're special. That's what life is about. You were special, Tony, to your mother, and you're still very special for many other reasons.
Yeah.
For many other reasons, but we have this artificial thing in our brain that says we're special, that we're unlearning. Right. I would go further by saying that the act for me of growing older is learning how unspecial I am.
Right.
And I think for science and for astronomy, that's the path that we're learning, how unspecial we are.
Well, I get it, and every time we have this conversation, you make me feel like I'm making that argument. I do not make the argument, nor will I ever make the argument that we're special. I do think, however, that the getting up to the various going through life stages and getting to a civilization stage is not trivial, and it is not a cakewalk to get where we are now, nor for a type 1 civilization to get where they might be now.
But let me turn that argument around, right? So the number of miracles that evolution has to go through, from the wet chemistry, from RNA to DNA, from to get cell membranes, each one of those, when we look back at it, as a miracle. Now, if it really is a miracle, how did we?
It's not.
How was it that 4 of them or 5 of those impossible things ever happened? And I think it's because we just don't fully understand the realm of possibility.
And I would be the first to admit to that, and I agree. And what I like about your technique here, with these heat signatures on planets to detect civilizations, is that you're not making any assumptions about the biology, about the intentions of the planet, as Svetlana has said many times, but you are just looking at something that, if you are a civilization, and if you are out there, and if you are putting out 10 to the 16 watts, then this will find it, and we will be able to get you and know that there's something there, which I do like. I think that's a much more robust technique than perhaps what SETI's doing, although I don't want to minimize what they're doing, nor say that they shouldn't do it. But I'm just highly skeptical. I'm afraid, Jeff and Svetlana, and I'll tell it to anybody who wants to hear it, of great filters. I think they happen, and that we still have yet to face one. That's what I think.
Well, I would like to say also this. Look, calculate the probability of you being born on this planet as you are now. It would be like unimaginably small if you take all these molecules in that way how we are. It's just impossible. Mm-hmm. It's magic that you're here. It's magic, but it happens.
Which is why we end up feeling so special all the time.
Exactly.
So before shifting entirely, I wanted to answer Mason's question because he might have a checkbook.
Yes, I was going to get to that. I was going to get to that next. So go ahead.
Yeah. Okay.
Okay. So Mason, we have actually a proposal out in the world to build a telescope. Oh, sorry. So Mason asks, how much money would an ExoLife Finder cost if you built it today? And so that's a scalable answer, but we have a real proposal out into the world to build a telescope that will look at Proxima b, the nearest exoplanet, the nearest star to the sun, and be able to make maps of the surface of that, plus many other larger and more distant, brighter worlds. And the answer is $25 million. And less than the cost of a Boeing 767, much less than the cost of a B-2 bomber.
Yeah.
It's
yes,
just takes the will.
It does. And as you've made a point quite a few times in the past that I didn't fully appreciate until I started doing these hangouts with you, is that these sorts of initiatives, like what the Planets Foundation is doing, have happened in the past from people like Percival Lowell and others. The big telescopes that we have that have Keck that have advanced astronomy have been privately funded telescopes, and that was something I didn't appreciate until I started doing this. So
I would say that even more strongly. I would say that all of the world's largest telescopes, when they were world's largest telescopes, were except for the Soviet 6 meter, were built by private money. So the Hale 100-inch. The Palomar 200-inch, the Keck telescope, the Yerkes 40-inch. All of these were created through mostly individuals, sometimes foundations, but never by governments or interagency governmental panels and hundreds of unwashed astronomers. That's another interesting point.
It is, and I never know how useful it is to ask this question, but I'll ask it anyway. Do you guys know roughly if the Palomar telescope that was built in the early 20th century, right, or the late 19th century?
yes.
Okay.
Yes.
Do we know how what you're planning to do with Planets Foundation compares in today's dollars with what those telescopes cost in those dollars? Does that make it? Is it a similarly scaled financial project, I guess, is what I'm asking.
It's actually,
it is.
no, it's cheaper.
Really?
So,
That's interesting.
Yeah. So if you were to scale Palomar and inflate the dollars that went into that, it was a few million at the time, you'd be within a factor of 2 of the cost of Keck. And the TMT project, the 30-meter telescope project, if it really ends up costing, what, 1.2 billion, is similarly of the same magnitude inflated from the Keck costs, depending on when we actually build it. So it's interesting that even though we've gone from millions of dollars for a telescope to billions of dollars, the inflated costs of these are not too terribly different.
That's interesting. And so the Planets Foundation is a bargain.
That's what I also
considered. All right. Any other questions you want to read, guys, or comments that you guys are scanning them too? I'm going through.
Would there be other science this project could, in addition to looking for ExoLife? Oh, sure. There are so many things you can do with those telescopes, because you look at stars also. So you look at the bright star, and you look for variability of a star and a planet, and you look at that combination, very close objects together. So you can learn about star a lot, and you can learn about the planet itself. Yeah, and you can look at point-like sources of other types, like asteroids and galaxies, like to learn about the composition of those objects.
So Care Bear's question was about the other science, and we won't easily look at galaxies unless we get laser guide stars to work.
Read the question. Will there be other science this project could, in addition to looking for ExoLife?
Yes, I kind of said
professionals like you, Tony. So the answer is, for looking at stars, there's really, right, we're stuck not being able to see any other star with the same detail that we can see the sun. And if we build an ELF, we will be able to see a few stars with resolution, not like we see the sun, but to be able to see the surface of the star. And that's a pretty exciting thing.
Actually, but I actually did this scaling. We will see other stars as Galileo saw sun with his little telescope, you know. Wow. That would be kind of resolution. And, you know, we can do study of the solar kind of activity on other stars, like Galileo did, and he made so many discoveries. You know, we'll make those discoveries with the stars. definitely.
Okay, well, John Suffol's over on Twitch, and he's saying the Russian 238-inch was built for one reason, to knock the 200-inch Palomar telescope out of the record books. So, but that was not privately funded. So, good job,
It was
John.
governmental,
Yeah.
yes.
Yeah. Okay.
But also it didn't. I mean, Svetlana will disagree because she's knows
It's
it
operatable.
It's operatable, but
it's operating. I should say it in English.
but it was a design that had thermal, and I mean it was really the limit of monolithic, large. Stiff
this is
mirrors.
1970s technology, okay? Even 60s probably. It's very thick mirror. I saw it. I was there visiting once. It's very thick mirror. I don't remember how thick, but it's really thick, and. So it's technology 1960s, 1970s, and that is a stiff mirror. There was no active optics in those times, you know. It was a stiff mirror, no adaptive optics.
Be careful. Be careful. The Palomar telescope has an active optic system. It's a mechanical system.
Well,
of
it's mechanical, but it's not so flexible as VLT, for instance. VLT was the first project when mirrors became much thinner. VLT is like this, 8 meter in diameter, is 20 centimeter thickness, and they introduced this much faster active optics.
The Keck mirrors were really the thinnest aspect ratio. Keck came in the 80s.
And
I would
improved,
wonder about JWSTs now, but that's a different topic. So, okay, I guess we're gonna call it a hangout. We are 2 minutes over, but I want to mention before we go one more time about the Kickstarter campaign going on for the Planets Foundation. They are trying to raise some money to get new materials made. You want to comment on that one more time for those who maybe didn't catch the beginning, guys?
Kevin?
Yeah.
Yep.
Yes, so Kickstarter, it ends October 8th, and just go to Kickstarter.com and search ExoLife Finder to find it, or it's in the description.
Great. And so, yeah, please do what you can to advance this project. It is absolutely worth your time and money, because what these guys are doing is nothing short of one of the most important problems we're facing in astronomy, and if they can do even a fraction of what they're trying to do, if they can just do one thing, which is find life elsewhere in the universe, anywhere, that would be the biggest thing that would be the biggest discovery ever in the history of all that there is. How's that?
Yes, thank you.
And
I want also to mention there's lots of amateur astronomers watching this hangouts that we try to make cheaper and cheaper. So it means that amateur astronomers also at some point gain an opportunity to have 1 meter telescope size for affordable amount of money.
You know? You mean as far as the technology spin-off, kind of like what NASA does?
Yes, absolutely. We kind of don't say that somewhere, but we were talking about that at some point, that this we were thinking to design like 1 meter of access telescope for amateur astronomers, which they can just buy for several $1,000s. You know,
think about it, a meter class telescope in your backyard.
Yes, absolutely. And what we just need is to create this meta material and test it. And this is our Kickstarter. We need just a few $1,000s to finish that.
All right, folks. Well, I want to thank you guys. Thank you guys very much. We'll stop it there. I want to. We're still putting together next week's. Or in 2 weeks, we'll be back with our next ExoLife Hangout, which I think Kevin and I are still putting together. Right, Kevin? Okay, great. Okay, we were soon to have a new topic for that. So thank you, Kevin. Okay, I hope you guys will tune in tomorrow. But we're back with Future in Space Hangout, where tomorrow we're going to be talking about the folks at right now. What astronomers in space astronomy are busy working on is the next decadal survey, and they are quickly putting together their proposals for NASA. And well, it's not just NASA, but for astronomy in general. And the case is being made for the Habitable Exoplanet Imaging Mission, or HABEX. And we're going to have members from NASA's JPL here tomorrow to talk about what they're doing and what they're hoping to get funding for with HABEX. So please join us tomorrow, 3 o'clock Eastern Time, for Future in Space Hangout. So thank you guys very much. And that's it. I want to thank you guys. Thank you, Svetlana. Thank you, Jeff. Yeah. All right. Okay. Yeah. Thank you guys very much. And thank you all for watching. And as always, keep looking up.